Now let's look at another way to combine vectors when we're adding. And in order to do that, we're going to need a few more concepts and notations to make our lives easier. And let's start with defining what a unit vector is. Well, a unit vector is pretty much exactly what it sounds like. This unit vector is a vector with a magnitude of 1. So 1 unit can point in any direction, up, down, 25 degrees. But the particular unit vectors we're going to be interested in are unit vectors in the horizontal and vertical directions. And we're going to have special notation for each of those. Here they are. The I vector will be a horizontal vector with a magnitude of 1. And the j vector will be a vertical vector with a magnitude of 1. How do we resolve a vector into horizontal and vertical components? Why would we ever want to do that? Well, let's say we have this vector, starting somewhere, ending somewhere. We can think of any vector as the hypotenuse of a right triangle, because we could draw a horizontal vector here and a vertical vector. So we would have so many unit vectors horizontally and so many unit vectors vertically that if we added them together, we would end up with our original vector. Let's take a look at a quick example. Suppose an airplane is climbing with a horizontal velocity of 300 miles per hour and a vertical velocity of 170 miles per hour. And we'll let I and j be those unit vectors in the horizontal and vertical directions respectively, which, as we just said, means that each of the vectors has a magnitude of 1 mile per hour. So we can describe the plane's motion as the resultant velocity vector, the sum of 300 unit vectors in the horizontal direction plus 170 unit vectors in the vertical direction. So we start by drawing our 300 units vertically or horizontally and 170 units vertically. So here's my 300 I and my 170 j. Notice how they're connected head to tail. And our resultant vector, where we started to where we ended, would be my vector v. With a certain angle theta. So that's how we would depict this final vector v. If we look at a standard question, let's say vector A has a magnitude of 3 and a direction 143 degrees from the horizontal. So let's draw that vector. A magnitude of 3 and an angle of 143 degrees from the horizontal. So if we do our horizontal line here, we would say that we have this angle of 143 degrees and a magnitude of 3. How do we describe this vector in terms of its horizontal and vertical components? So how do I find this horizontal and this vertical information? Well, since we've created this right triangle with a hypotenuse, we can use SOHCAHTOA. The cosine of 143 would equal our horizontal information over our hypotenuse. So our horizontal would be 3 times the cosine of 143. And if we use the same logic, our vertical ends up being 3 times the sine of 143. Doing the math, we find out that our horizontal component is negative 2.396 steps in the horizontal direction. We can think of that I as a single step, and 1.805 steps in the vertical direction. So if we look at what we did there, we can see that converting from a magnitude and a direction is a simple formula where we take the length of our vector times the cosine of theta to find our horizontal component, and we take the length of our vector times the sine of theta to get the vertical component. Now, where this approach comes in very handy is when we are trying to add vectors. If we take vector A being 5 at 70 degrees, so let's start with that vector. Here's 5 at 70 degrees. We're not going to be too worried about the scale, but we're thinking about the direction. And vector B being 6 at 25 degrees. So here's vector B being 6 at 25. But we want to find the resultant vector R, which means that we need to add these two vectors, so we need to connect them head to tail. So what we're going to do is find this resultant vector. But we're going to find it by breaking these two vectors down into their components and adding their components. You'll notice that if I take my first vector and create the two vertical components, create my right triangle, and I do the same thing with my second vector, my final vector here, whose right triangle looks like this, is the sum of the vertical components. So this vertical component plus this vertical component gives me the larger vertical component of my sum. And the same thing with my vertical components. If I take this vertical component and add this vertical component, I end up with the vertical component of my final resultant. So the first thing I do is break down each of my two vectors into their components using our formula. So the first vector is 5 at 70 degrees. So vector A is going to be 5 cosine 70 I plus 5 sine 70 j. For vector B was 6 at 25 degrees, so we just quickly break that down. 6 cosine 25 I plus 6 sine 25 j. And to find our resultant vector R, we just add the components. So we get the sum of these, which turns out to be 7.148 I plus 7.234 J. So we have this sum or resultant in terms of two components. Now, to find the magnitude and angle, what we recognize is that those two components, again, are the sides of a right triangle. So we take these, and to get the magnitude of R, it's just like finding the hypotenuse. So 7.148 squared plus 7.234 squared, square root. which is approximately equal to 10.170. To find the angle, we use SOHCAHTOA, and we say that the tangent of theta would be the j component, or vertical component, over the horizontal component, opposite over adjacent. And that's 1.012, which means that theta would be the inverse tangent of 1.012, which is approximately equal to 45.344 degrees.